All right, looks like I'm a little blurry here. There we go. That looks a little better. Okay, let's get started. So, stuff to talk about. Well, excuse me. As soon as I start talking, I get all realize I have all this congestion. Okay, so where are we in the class? We're kind of entering those last days. It may seem like the final exam is way far off, but it's not, partly because of holidays. We only meet about 6 more times, including today. So, um, you know, hopefully you're really starting to formalize your ideas for your project, because it's going to be much harder to get a hold of me and get help towards the end of the semester. I do have office hours and stuff like that, but my office hours tend to get busier, and then you're sort of waiting in line. So those of you who are doing a little bit of work ahead of time, avoiding that procrastination, are more likely to get the help that you need in order to get that extra bit of points on your final project, right? And I have some students doing that, coming in and asking me questions, and I help them, and they go, oh, okay, I understand what you're saying. And then they go back and they rework their stuff. And it doesn't even take that long, because it's not like they're starting from scratch. They just go back and they're like, oh, yeah, he said I should do my graph this way. I should make sure I include the regression line. I should do these things. And then, StatCrunch makes it pretty easy, but all of a sudden your presentation is so much better. Even though it only took, maybe it only took you 30 minutes, and you've now, going back and improving things a little bit, and you just turned a C project into a B project, or a B project into an A project. What I can tell you is, trying to do that at the last minute, you're going to be more on your own doing it, because that's just the nature of things. Like, sometimes during finals week, students are wanting to meet with me, and sometimes I can accommodate that. But, finals week is pretty busy for everyone. It's just a wild time for students. It's also pretty wild for instructors, because our schedule's all messed up. Stuff's happening at different times, and there's, and then we're supposed to get grades in as soon as we can, right? Because ultimately, students need those grades turned in as soon as they can, because you need transcripts sent out to other schools. You need financial aid to know what your grades are, all sorts of stuff. So there's a lot of pressure on us to get those grades in ASAP. So that's kind of what gets focused on in finals week. So please come to me now in the next couple weeks with your questions, so that we can have discussions during office hours about, are you on the right track? Are you doing the right things? How can I make some suggestions that would make your work a little bit better? Any of that kind of stuff, is going to come across in that final presentation. And make sure you know how you're making your video, right? There are tons of ways of doing this. There are free products where you can do a screen capture and put a voiceover in there, where you can do it with your phone. There's lots of ways of doing it. Just make sure, if you're going to take kind of a low budget or a low tech approach, that you really do the best job you can. Like I say, I've had students where they take their phone and they probably not hold it, because then it's moving and it makes it really hard to see what's going on. But students will have a stand or something, so they're videotaping with their phone, looking down on some graphs that they made. I've had that work, but those graphs that those students made were really good, like really good, right? It wasn't like, oh yeah, I just took a couple minutes and I threw this graph together. Like, they looked like, almost as good as a printer version. I would highly recommend you just print them. It's much easier. It's much easier to print them, and they're gonna look better. It's gonna look more professional. So, and then I can focus on the actual material. If I'm distracted by, I can't quite see your graph because your camera's moving, or I can't really see your graph very well because it's too dark in the room, or I can't really see your graph because you did a whole histogram in like a minute, and I can't really make sense of it, those are things that are going to hurt you. But so you want to do a good enough job that I can just focus on the statistics. Like, does this person know what they're talking about with statistics? Because if I don't see information conveyed to me, I have to assume the reason that you didn't put it in your video is because you don't know it, right? You're supposed to show me how all these tools we've been learning fit together into the project, okay? So make sure you're thinking about that. Moving forward, trying to do this at the last minute, not a good idea. I did get caught up on a little bit of grading yesterday, so just a few extra grades popped up. We do have 6 more meetings. What we're going to do is, and we have an important one coming up where there's actually a quiz that I'm going to have to give you that is worth some points. It's not really going to move your grade very much, but I have to make it worth enough that people take it. Otherwise, people kind of skip it. And it's a quiz that we have to have for accreditation. There's this thing called student learning outcomes, and we have to prove when accreditation comes next year, we have to be able to prove in our classes that we're teaching certain topics and that it's effective. And so it's actually really important. It affects the accreditation of the school, which everyone is interested in. So we're going to circle back and talk about correlation and regression towards the end, and then you're going to take a quick quiz on it. And don't panic. If you understand the basics of correlation, if you understand the basics of regression, you'll be fine. And like I say, I'm going to spend a whole class period talking about it, and then you're going to take your quiz, okay, on it. So if you go, well, I don't know, we talked about that a few weeks ago, I don't remember, we're going to review it, and then we're going to look at it, and then you'll take the quiz, and then we'll sort of go from there. So that's coming up. That will take a day. And then we've got hypothesis testing we need to talk about. That's probably going to take a couple of class meetings. And then we're still talking a little bit. There's a little bit more I want to say about confidence intervals, which some of you may fully be comfortable with confidence intervals, but my guess is not. So I will have more of a discussion about that. Those are kind of the main things we need to get out of the way. And then we'll be wrapping up the course. You'll turn in your projects. Some of you will get A's on your projects. Some of you will get failing grades on your projects. Some of you won't turn a project in. So there's kind of a whole range, but that outcome at the end is sort of being developed now, right? So sort of preparing for it now. Please don't try to do your project last minute. It ends up in a poorly executed project, right? Okay, so with that said, let's jump ahead. I did have to use a different textbook, so it looks a little different now. This is the 11th edition. The PDF I was using before got taken down. So here's a different one. And I just kind of want to explain a little bit, right? You might have said, yeah, we talked about this, and I get it. But you're going to hear me repeat things because confidence intervals are a thing that students get confused about, and they think they understand it, but they really don't. And then hypothesis testing is a big one where most students, they just know they don't understand it, and so they try to memorize how to do it. But I really want to make sure you understand hypothesis testing. It is the most complex concept of the course, I would say, because the logic and the way you think about a problem and the wording that we use is very precise. And if you state it incorrectly or you do it a little bit the wrong way, your hypothesis test won't be valid. It doesn't really make sense at that point. So want to make sure you understand it. And it's a big deal for the project because, most of you will probably get a confidence interval fine, although I do see students who present me confidence intervals on the project, and it's clear they don't understand what it is. They just say, here's my confidence interval, and then they move on. You should summarize. You should be explaining and summarizing what those objects are. So when you give me a confidence interval in your project, tell me what it means. Don't just say, my confidence interval for this question is from 2.54 to 3.71. Okay, that's like a very low grade paper. That's like putting you on track for C/D kind of project. Okay, giving me a confidence interval and saying, well, this was the mean that we found. And when we calculate a 95% confidence interval, we found that we are 95% confident that the true proportion of students who blah, 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 whatever your project is, falls between this amount and this amount. So so we think that it falls in that zone. That kind of an explanation, at least I know, this person knows what a confidence interval is, rather than someone who just watched the video and pushed some buttons in StatCrunch and made a confidence interval and then just read that confidence interval in their video. That's like very minimal, right? That doesn't mean you understand anything. It just means you looked in the book and pushed the same buttons they told you to push, but it doesn't show that you actually understand. So make sure you're watching those videos. See how in the videos they're explaining what their confidence interval is. Just model your problem after that. So when you're watching the videos and they'll say a sentence summarizing a confidence interval, write that sentence down. Even if you have to pause it a couple times, write that sentence down and then look at the wording and go, how can I change the wording of this sentence to apply to what I'm doing? And then not only will you start to make sense of it, but it will so you'll learn it, but also you'll be able to state it in your project so that I know that you learned it, right? If you're just stating a confidence interval, what we would do in the classroom if someone just said, here's my question, and it gave me a confidence interval of this and this. And then my question would be, what does that mean? Can you explain to me in a couple sentences what it means that your confidence interval goes from this number to this number? And sometimes the answer is no, right? And I don't mean that I'm like trying to embarrass the person or anything. I'm talking about when we're doing problems and I walk around the room and I'm helping people. Oh, can you explain to me what that means? No, but I calculated the confidence interval. You might as well not be in a stats class if you're doing that, because what's the point of being able to calculate a thing that you don't know what it means? It literally is a big waste of time. You'll never be able to make sense of it in the real world. So that's why it's really important that you understand what a confidence interval is, and that you give me that explanation in the project. Same with the hypothesis test. Don't just read me a hypothesis test. If that's all you do, then I'm going to say, this person, what this person learned how to do was push some buttons in StatCrunch. They didn't learn what a hypothesis test is or how to use it. But we'll talk about that when we get into hypothesis tests, which we may start today, but it may wait until Thursday, right? Yeah, Thursday as well. So we'll have to see. So I just want to return to this example. It's been a week since we met, and I just want to make sure everyone kind of understands what's going on here. So these are confidence intervals that people came up with. So really what happens is, let's say this is our problem that we're working on for the smoking. I just go back to that because we're familiar with it. The tobacco smoking ban on campus and the vaping and all that kind of stuff that they went forward with. So let's say that I sent each of you out and said, ask 100 people if they support the tobacco ban or not. And let's just say that the true proportion is 0.75. But that's an unknown value. It's basically, most of the time, it's impossible for us to ever find that the true proportion is 0.75. We don't ever know. If there was a magic tool where we could know, sometimes because of the way we teach math, people get the wrong idea of how math works, because many of you grew up looking at the answers in the back of the book. So there's this idea that, well, when you do math, you have to struggle with it and you don't know what's going on, but there's this knowable value that exists in the world that then you look up the real answer. You see if you can do it, and then when you can't, you look it up. But as someone once stated, in the real world there is no back of the book, right? There is no place where you go and see if you're right. It's just you'll see, because your business will actually succeed in the way you think it is when you start implementing the things that you figure out financially, mathematically. If you do them wrong, then your business is going to be a mess, right? So you never really get to know this, and that's the frustrating thing about the statistics, is we never know that the true proportion is 0.75. We just want to build a lot of evidence that it's around 0.75, okay, that we think that's where it exists. But a lot of times I get the sense when I'm talking to students that they think we're doing all this, and then when do we just get to see what the answer is? Well, that's the problem. That's one of the hard things. That's why statistics exist, because you never get to know the true proportion. It's not like you ever find it out. Someone doesn't come to you later and say, yeah, you've been working on this for a week. Here's the real proportion. Did you get it right? That's the whole point, is that we have to come up with our best guess for what that proportion is. So let's just say the true proportion of students on campus who support a full tobacco ban is 0.75. Okay. Now, these were confidence intervals, but remember how a confidence interval works, is that the center is actually the point estimate that you came up with. So that's the middle of each of these lines, each one of these vertical lines would be a confidence interval that each of you came up with. The center of that interval would be the actual proportion that you measured. So some of you would go out and you would ask 100 students if they support the tobacco ban, and some of you would come back and say, I think the proportion is 0.73. That's what I measured. And someone would say, I think it's 0.77. And someone would say, I think it's 0.80. And someone might say, I think it's 0.69. Like, you're all going to get different values, right? That's part of the issue of random sampling, is you're all going to get a little bit different values. Some of you might get 0.75 as your measurement, and some of you will probably get things that are around 0.75. But almost all of those point estimates are likely to be wrong, right? You might get 0.745. Someone might get 0.764, right? You get all these different values, and they're off by a little bit. So what we do is we create an interval, and we say, my point estimate is probably wrong. But if I create an interval around my point estimate, I'm likely to have the true proportion falling in there. So that's what's happening, is each of these lines would be a different student. You measured your point estimate, and you made, say, a 95% confidence interval around your point estimate, and see how most of them overlap the true proportion. So if it's a 95% confidence interval, then 19 of the 20 people we would expect would be right that the true proportion lies somewhere in their interval. And again, the mistake that some students make is they go, oh, well, if the proportion lies inside my interval, then doesn't that mean I can just find the middle value, and that's the true proportion? No, that's a breakdown in logic. That's a breakdown in the critical thinking. You're getting very circular there. We constructed the confidence interval around your point estimate. The point estimate is going to be the middle. So if you go back and now find the middle of your interval, what you're going to get is your original point estimate, but we already said that point estimate is probably a little bit wrong. That's the whole reason we created the confidence interval. So I see students go in this loop where they go out, they measure a proportion, they come back and they say, I'm going to build an interval around this proportion. Now I'm going to find the middle of that interval and say that's the true proportion. But that's just the original proportion that you measured in the first place that we knew is probably close, but not the right value. That's the whole reason for creating a confidence interval. So don't go in that loop. Just follow the directions, which are take your point estimate, which is the proportion that you measured in the survey, and then around that create a confidence interval. Don't try to break it down further, because that doesn't hold up mathematically. Okay. Now what about this person? Well, with a 95% confidence interval, you expect to be successful 19 times out of 20. In this case, successful means that the true proportion is actually in the confidence interval. But what you have to realize is we never know. We don't know for sure. If there's 20 of you that went out and created intervals, and you did 95% confidence intervals, then we would expect that one of the 20 of you is wrong. But in real life, you never know who this person is. It's not like I can point over in the corner and go, sorry, Jane, you're the one whose confidence interval is wrong out of the 20 people. And I just made up that name, Jane. I don't know if there's anyone in the class named that. So it's frustrating because we're so used to math classes where everything is known, everything is knowable. But in reality, it's kind of fake. In reality, like, that's the learning process. We're giving you problems that we know the answers to, but in real life, you don't get to know the real answers, right? If there was a way of knowing those things, we would do that instead, right? We wouldn't do all this work and then say, okay, now give me the real value. We would just go right to the real value if it existed out there. We have to come up with our best guess for what that real value is. So in a 95, if 20 people construct a 95% confidence interval, we expect one of them to be wrong. That's the person right here. People have, you hopefully by now have a much better idea of how probabilities work. Most people are not good with probabilities. They think that if something has a high probability, they just kind of go, well, that's pretty much going to happen all the time, right? No, a 95% confidence interval means it's right 95% of the time. That means it's wrong 5% of the time, right? This is why everyone freaked out and didn't understand polling after the Clinton Trump election, because the statisticians and 538 and those places, they gave Hillary Clinton an 80% chance of winning. That means she has a 20% chance of losing. That means she loses 1 time out of 5. Right, and she ended up losing, and everyone was like, "Oh, but the but she was supposed to win. She had an 80% probability of winning, right? Which leads to a 20% probability of losing. So just because something has a high probability of occurring doesn't mean it's going to happen every time. This is a thing that I run across with students where they have some kind of block where it seems like we teach people from a young age the wrong way to think about probabilities, and then it carries over to when students actually start to learn about probabilities. They're still carrying some of this baggage from when they were younger and were taught to use probabilities in the wrong way, or just never were taught to use probabilities. So in a 95% confidence interval, that means you're 5% uncertain, right? Which means you're pretty sure, but sometimes you're going to be off. Now, so out of 20 people creating these confidence intervals, notice that there's one that is wrong, but 19 of the 20 people are correct. But again, that true proportion falls in different parts of the interval, right? And so what you could do is you could go, well, then doesn't that mean when we conduct a survey that I should repeat it multiple times? Yeah, it sort of does. But in reality, that doesn't usually happen. Right? In reality, we're probably not going to do 20 versions of polling people at the college. Okay? What would happen is we would just collect 1,000 or 2,000 people. We would say, go out and talk to 2,000 different people and get their results. It would just sort of be one large sample, and we'd have one big confidence interval. Is usually how it's done. So it's a little misleading, but we kind of end up in a similar place, right? So this picture actually tells a lot about confidence intervals. That's why I've talked about it last time. I'm talking about it again. If you can really understand what's going on in this picture, then you probably have a fairly good understanding of confidence intervals. Okay, and just recognize this red one. This person is sitting there thinking, I think the true proportion of students who support a full tobacco ban falls between, what would this be, like 0.67 and 0.72, except they would be wrong because the true proportion falls between 0.75 outside this confidence interval. They're wrong, but they're not going to know they're wrong, right? But then we would look at these other 19 people and see, well, they fall in this zone. So, we would probably maybe take I don't know. It's hard to tell because, again, you never get to see this graph. You never get to see this line where the true p-value is, the true proportion. You never get to know that. So it's harder when you're calculating those confidence intervals because you don't really get to know if you're right or not. Okay. So that's an important thing to remember. Let's see. I'm not familiar with this new text yet. I didn't have a chance to sort of go look it all over. Where are we? So let's. Okay, so this is like what I'm talking about when you want to summarize things. Do not make your own. Don't just like sit down and go, okay, here's what the confidence interval says. Look at how they're describing it in the videos, how I'm telling you in class to summarize those things. Because if you summarize a hypothesis test or a confidence interval incorrectly, it makes that whole part of your project looks like you didn't understand it because you stated it wrong. So you want to make sure you're reading how you summarize these things. So let's look at this problem. This problem is about constructing a confidence interval from poll results. Pretty relevant to what you're doing, right? So in this one, you can see how this relates. We have in the chapter we noted that a Pew Research Center is one of these places that you can hire to do a poll for you. You'll say here's the poll I want you to take. They'll say here's how much it's going to cost, and then they will do their best to do it in a constructive way. Right? It's not like when Fox News does their own poll on their website and it's like, don't even sort of put any faith into it, or MSNBC or whatever. Pew Research does like legitimate polling. Okay. So they poll 1,501 randomly selected U.S. adults, showed that 70% of the respondents believe in global warming. Okay. So does that mean that the true proportion of people, adults in the United States that believe in global warming is 0.7? No, that's just what Pew Research Center measured in their particular poll, right? But it could be, where was that? I suppose I'm going to be jumping around here. Sorry, let me see if I can center this better. If we go up, probably the Pew Research poll is somewhere in here where they're going to create a confidence interval that contains this. But remember, the center of these intervals, I don't see any, that maybe a couple that look like the center is right on 0.75. That measurement that you take for your proportion is probably a little bit off, right? It could be this one. It could be that your whole confidence interval is going to be off. What page is this? 349. Oh, did I pass? Is this it? Uh-oh. Sorry, I went past it. Like I said, I'm still getting used to this version of the book. Where is it? Oh. Nope, it's down here. Oh, sorry, kept blowing past it. Okay. So construct a confidence interval around the poll results. So the true proportion is probably not 0.70, but it's probably around there. That is our point estimate. That is the sample proportion that we found. So we want to find the margin of error that corresponds to a 95% confidence interval. There's formulas for this stuff, but the good news is StatCrunch will just calculate a 95% confidence interval, which again is why that's not really that helpful that you can do that in your project, because it's the computer doing that, not you. You have to be able to understand what that thing means. So for us, we'll just say go into StatCrunch and calculate a 95% confidence interval. All right. Find the 95% confidence interval estimate for the population proportion P. So based on the results, can we safely conclude that the majority of adults believe in global warming? So think about that. Majority means more than 50%. So if we measured that 70% of adults believe in global warming, that was our measurement, it's probably pretty likely that more than half of adults believe in climate change, right? Because if the number was like 40%, how would we measure 70%? If we did our work properly, it's unlikely that we would be off by that much, right? If you're doing it right, 1,500 people, you wouldn't expect to be off by that much. So we feel like probably a majority, but we don't know if we can say that. We need the statistics behind us that can say, yes, you can make this statement that a majority of adults believe in global warming. It's not, our point estimate is not good enough because we could be off. So now we want to write here's how you should summarize these things. So, whoops, where'd the problem go? Here we go. So look at how they make their statement. 70% of the U.S. adults believe that the, wait, that's not our confidence interval though. Based on the confidence interval, so we made a confidence interval up here between 67.7% and 72.3%. Based on the confidence interval obtained, it does appear that the proportion of adults who believe in global warming is greater than 0.5, because that's the majority is 0.5. That's where the 0.5 number is coming from, is we're seeing if we can make it about a majority. So we're 95% sure that the true proportion is between 67.7 and 72.3%. Well, that's above 0.5. We're 95% sure that's true. So we can safely conclude that the majority of adults believe in global warming. Right? So does that make sense? Why we can say a majority of adults, but we had to have an interval that was clearly bigger than 0.5. What if we had come up with an interval that went from 0.48 to 0.54? Could we make that same statement? No, because it could be the true proportion could be 0.48, and that's below 0.5. So then we wouldn't do that. But if your entire confidence interval is above the value that you want to make a statement about, then you can say that, right? Does that make sense? If you're confused by that, let me know. So here's one statement that summarizes the results. 70% of U.S. adults believe that the Earth is getting warmer. They kind of can't completely say that. That percentage is based on a Pew Research Center poll of 1,501 randomly selected adults. In theory, in 95% of such polls, the percentage should differ by no more than 2.3 percentage points. So that's another calculation that you can make that you'll learn where you come up with that margin of error. And this is one of the things that's so silly is you'll see like, when it's election time and you have two candidates and they're like, and it's a really close race and they're like, well, here's our poll and it looks like, candidate 1 has now pulled ahead with 49% of the vote and candidate 2 has 48.5% of the vote. And then you look and there's a margin of error of 5%. And it's like your margin of error is large compared to the little narrow measurement that you're making. That's why sometimes in a close race from day to day, it seems like it's flip-flopping each day, and people tend to go, oh, man, society's really changing their minds each day. It's just that random variation from sample to sample that's being done each day that's actually changing. Probably not people's opinions that much, okay? So try to make some kind of a statement like here, how they do it here, where you take your confidence interval and you interpret that into something meaningful, okay? Right. And then there's sample size, which we won't have to mess with too much. You'll do a little bit of that in your homework. Where are we? Where's the next thing I wanted? Sorry, let me catch my place here. Okay. Here's also kind of a silly thing. We have... when we calculate means, there are two techniques for doing this. One is when the true sigma is known, and one is when the true sigma is not known. Well, so what was sigma again? That's our standard deviation. So imagine you have a set of data, and you don't know the mean. You want to come up with a representation for what the mean is, but somehow you know the standard deviation? How would that even happen? So this ends up being kind of a silly thing that gets thrown into these textbooks. Even if you're a professional statistician, you will probably almost never come across a situation where you need to estimate the mean, but somehow you know the standard deviation. I mean, just think about that. How would you get the standard deviation if you didn't know the mean? So we have a tool for calculating it in that case, but you almost never know that, right? So, so you can sort of ignore the part where it's... we need to know the mean, but we already know the standard deviation. That's very unlikely to happen. Oh, where am I here? Right. So 355 is the one we want. Sorry, I had to find my page. See how they have it in the beginning? You've got estimating a population mean when sigma is known, estimating a population mean when sigma is not known. The not known is the one that's actually relevant because that's what happens like 99.9% of the time. Or more. So that's the one we'll focus on for us. Oops, did I go to the wrong page? I did. That's the one I don't want. Oops. And the good news is, StatCrunch is going to do the right thing for you. So this is what we care about, where sigma is not known. Right. So as always, the mean that you measured, right? So we were talking about proportions before. Remember, a proportion you can loosely think of as like a percentage of people who do a thing, the percentage of people who support a tobacco ban, the percentage of people who are above a certain height, the percentage of people that have a certain belief. Those are going to be proportions. Now we're looking at the mean, right? So the mean, right? The sample mean, that is, you go out, you measure something, the mean that you measure, that's going to be your point estimate. Just like before, for proportions, the point estimate that we were going to use was the one that you measured when you did your proportion. That's the best thing you have to go with. That's the best information that you know. Well, here we're just going to use the mean that we measure for whatever it is the sample is that we're measuring. We're going to use that mean as that point estimate. Now, there's a little bit of history that goes around this, but you get to skip most of that. When you do this, you're actually using a thing called the student t distribution, which has sort of been updated over the years to just have, because when the first student t distribution came out, there was less technology. Now we can have a much more filled in distribution, but it's just kind of an interesting history. Basically what happened was, and StatCrunch does all this for you, but there was an individual working for the Guinness Brewery, and he was trying to do quality control, right? This is a thing you do. Most companies, when you manufacture a product, you have a person or a group of people in charge of quality control, which means they make sure that all of a sudden you're not sending out junk, right? Let's say that you have a so they actually did this in one of the episodes of The Office where Creed was actually the quality control individual, and he got in trouble for not taking care of that. So what would that mean? Well, let's say you have a paper company and you're manufacturing paper, right? Which they didn't do on The Office. They just sort of distributed the paper. But let's say you manufacture paper. So you have a company that's just spitting out paper all day long. Okay, well, that's great. You have good paper coming out. Well, then all of a sudden, one of your machines develops a little oil leak in it. So every time a piece of paper would come through, there'd be a tiny little speck in the corner of oil coming from this machine. Well, the company, say imagine a large company, maybe a hospital that has a lot of paper they have to print all the time. They're not going to like it if they get this shipment of paper and every single piece of paper has a little tiny little oil spot in the corner. They're going to go, we paid for like good paper. Why are you giving us something that has a little stain in the corner? So quality control means that someone is watching that quality so that when something does occur, like a machine not working right, somebody who's watching will be able to pull that paper and go, uh-oh, we have a problem, everybody. This paper has a flaw in it, and all the paper coming out right now has a flaw in it. We need to stop production so we can figure this out so that we're not shipping out flawed paper, because once you deliver that flawed paper to the hospital, they complain. You have to go get the old paper, bring it back, and then deliver them the new proper paper. That's a huge pain. So you want to stop that paper from even being produced so you can fix the problem before it ever occurs. So you need someone watching and then saying, all right, what if you do find a speck on a piece of paper? Then you're scratching your head and you're like, was this a one-time thing where a bug just crawled onto the machines and then got squashed? Or is this a thing that is like a recurring problem, right? That's part of what this William Gossett wanted to know, who worked at the Guinness Brewery. Now, just like today, where companies want to have full ownership of everything because they want to have every possible way that they can profit in their business, they do. So a lot of times that means not releasing information. So they didn't let, even though this William Gossett was coming up with really important statistics, the Guinness Brewery had a rule that says you can't publish information. Everything that we come up with gives us a business edge. So the world you can't tell the world about this. We have to use it to try to gain our advantage in the company. So he wasn't allowed to publish the work. So he came up with a name called student. So it's kind of unfortunate. There's so many things in math that are named, unfortunately. The student t distribution, people think that that's some kind of like thing we use in education. It's a thing we use everywhere. It's just that this guy published it under the name student. William Gossett published it under student because if he published it under his own name, Guinness was going to fire him, right? So he took this and published it under student so that the world could have this information, and it's called the student t distribution. And that's what the behind the scenes inside of StatCrunch, when it's creating this, there's a student t distribution in there being used in order to create this this work that we're doing to come up with these confidence intervals for the mean. So just kind of know that. And we can come up with a population as a normal distribution, then the distribution of t equals this. You don't even have to worry about that. StatCrunch is going to do it all for you. There is a term, degrees of freedom, that you need to know. In general, the degrees of freedom is n minus 1. So remember, n is whatever your sample size is subtract 1, that gives you your degrees of freedom. It won't really come up, but sometimes you'll hear that word degrees of freedom. You go, what's going on here? Just subtract 1 from your n, and you'll have it. So basically we get, it's similar to the confidence interval that we had for proportions, but it's a confidence interval for the mean. Okay. So for instance, like when you're brewing, right? When you're brewing beer or something like that, there's a thing called specific gravity. And I don't know, they don't put the details in here of what was being measured by the person at Guinness, but there's a thing called specific gravity, right? If any of you have ever brewed beer before, you don't have to do this, but it's optional. You can make a measurement of what they call specific gravity. You can think of it loosely as the density of the beer. You go, isn't beer just always have the same density? No, depending on how you brew it, there's little changes in that beer, and it's one way to help you measure alcohol content. So, if you get down to a molecular level, every glass of beer is slightly different. There's a slightly different alcohol content in every bit of beer, but it's all more or less the same, right? You would have to go a lot of decimal places before you really start seeing a big difference in the alcohol content, as long as you have good quality control. So that's, we could measure that. We could take a barrel off the line, measure the specific gravity, and then create a confidence interval around that and figure out, like, what do we think the true specific gravity of all this beer coming off the line is, and then you could see, are all our barrels matching that? So you could test your quality control, right? So it's really, if you understand the idea of confidence intervals for proportions, it's basically the same thing for the mean. Now, it uses different formulas for the mean because it's different type of data, and it's done in a different way. But again, you don't have to worry about that because you're just dealing with, you're having StatCrunch do it for you. One thing that we do need to have in general is that your sample size, so here's a requirement, your sample size either has to be normally distributed. So if you have a normally distributed population, then you're fine. But what if you don't have a normally distributed population? What if your data is skewed? Then your N has to be bigger than 30. So, that's a little bit of a problem for those of you in the survey. Did we have 30 people? I've got my 3 classes. I forget which way it lined up in here, but you might not have 30 people. That doesn't mean abandon everything and don't make confidence intervals, but you might mention, unfortunately, we didn't have 30 people, so this, we're a little bit dubious about our confidence intervals, right? Don't try to hide stuff like that. You want to put the weaknesses out there so that people can judge them. And also, when I'm watching your video, I go, oh, this person understands that they don't have enough people to really trust their confidence interval. That's good. Right. Let's see. I have 5 minutes. Let's see what I can get into. So you can see they use it for all sorts of stuff. Estimating sugar in oranges. Estimating if garlic actually reduces cholesterol. All this kind of stuff. You can use these confidence intervals for lots of things. You don't have to do any of that. Oh, one thing I'm seeing, some of you, when you got to your regressions and your correlations, are not including the line in your scatter plot. That is a thing that when I see that in your final video, I'm going to wonder why. Why didn't they put the line in there? Why didn't they talk about that regression line? It seems like they're missing a whole thing. Now, you may put the regression line in there and go, see how bad it is? Like in this case, this is not a good regression line. That's fine. Put it in there and go, it doesn't look like this line fits our data, and here's why. That shows me that you know what you're talking about. So make sure you're including that line of best fit. It's just if I remember right, it's just a check that you put when you're making the scatter plot. It's like, do you want to include the linear regression? Yes. And you just click it and put it in there, and it does it for you basically and gives you the formula. So, but you don't want to be missing that. Let's see. Is there anything else I can say before we're done? No, looks like that's it for today. Right, and we won't do that one. Okay, so next time we talk, I think we're going to start talking about hypothesis tests, unless I decide we need to do something else in the meantime, because actually we'll have Thursday and Tuesday to get through a bunch of that. So that should be okay. So yeah, we'll start talking about hypothesis testing next time, because it's going to take us a while to get through it. Anyone who wants to ask me any questions, please hop into Zoom and speak with me about whatever you want. Otherwise, I will see you in a couple days. All right, thanks everybody.